All right, today we're diving headfirst into a world. A world where everything you think you know about reality just gets thrown out the window. We're talking about the weird, the wonderful, the totally mind-bending world of quantum mechanics.
So let me ask you something right off the bat. Are you a particle or are you a wave? Now, I know that sounds like a totally bizarre question, but stick with me because in the quantum world, the answer is, weirdly enough, yes, both. And getting your head around that idea is the key to unlocking everything else we're going to talk about.
Okay, so where does this all start? Well, the whole game changed when scientists realized that things we always pictured as these tiny solid little balls, things like electrons, could also act just like waves. And I'm not talking about a small adjustment here. This was a complete tear up the old textbooks kind of revolution for physics.
And the guy who really kicked this door wide open was a French physicist named Louis de Broglie. His thinking was just beautiful in its simplicity. He basically said, hang on a second. We know light waves can act like particles, right? So why can't particles act like waves? It seems so obvious in hindsight, but that one question, man, it changed everything.
And de Broglie didn't just stop at the idea. He turned it into an actual equation. And what it tells us is pretty wild. It says that everything, you, me, this planet, everything has a wavelength. But here's the catch. That wavelength is tied to its mass. The more massive something is, the tinier its wavelength gets. Like ridiculously tiny.
And this is where you can really see why this matters. Think about a baseball. Does it have a wavelength? Yep, but it's trillions upon trillions of times smaller than the nucleus of a single atom. It's so small, it's completely meaningless in our world. But then you look at something tiny, like an electron. For an electron, its wavelength is actually pretty huge compared to its size. So for the electron, being a wave isn't some weird little quirk, it's a fundamental part of what it is.
So what's the big takeaway here? It's this. That whole wave-particle duality thing, it's not just for light, it's for everything. It's a universal rule of the cosmos. Everything is both a particle and a wave at the same time. The only reason we don't see a baseball acting like a wave is because it's just too big. The weirdness is always there, we just can't see it on our scale.
Okay, so if an electron is a wave, what on earth does that do to our picture of the atom? Well, it pretty much blows it up. And this is where another giant of physics, Erwin Schrödinger, steps onto the stage.
See, Schrödinger realized the old physics just couldn't handle this new reality. So he built a whole new rule book, and that rule book is what we call quantum mechanics. It's basically the math you need to navigate this bizarre, wavy world of electrons and other tiny particles. You know that picture of the atom we all saw in school, the one that looks like a mini solar system? You've got the nucleus in the middle, like the sun, and these little electron planets zipping around in perfect orbits. It's simple, it's neat, it's tidy, and it's totally, completely wrong. The real picture, the quantum picture, throws that whole idea in the trash. Instead of a tiny dot whizzing around, you have to imagine the electron as a cloud of probability. I know, that sounds complicated, but all it really means is that we can't say the electron is here. Instead, the cloud shows us all the places the electron could be. It's not a planet in an orbit, it's more like a smear of pure potential.
And if you think a cloud of possibility is weird, hold on. Because this idea leads to something even stranger. This fuzziness, it isn't just about where an electron is. It's actually a fundamental limit on knowledge itself, a limit built into the fabric of the universe.
This is the famous uncertainty principle from Werner Heisenberg. And the most important thing to get about this is that it's not about having bad instruments. It's not like, oh, if we just build a better microscope, we'll figure it out. No. Heisenberg showed that it's a hard and fast rule of nature. The universe itself puts a limit on what we're allowed to know at any one time. And this quote nails it. Think of it like a cosmic seesaw. The more you know about where an electron is, the less you can possibly know about its momentum, how fast it's going and in what direction. And if you nail down its momentum perfectly, its location becomes completely fuzzy. You can have one or you can have the other, but you can never, ever have both with perfect certainty.
So let's be absolutely crystal clear here. This isn't a bug. It's a feature. This uncertainty is not some problem we need to solve. It's a direct consequence of an electron being both a particle and a wave. This fuzziness is just how the universe works at its most fundamental level.
Okay, I know what you're probably thinking right now. This is crazy. This makes no sense. And you know what? You're right. It completely defies our everyday common sense. But that's the thing.
Our common sense is built for a world of throwing rocks and catching baseballs, not for the bizarre world of subatomic particles. To understand that world, we have to trust something else entirely.
I mean, how can any of this possibly be true? A particle is a wave? There are things we're literally forbidden from knowing? It feels like it breaks the very rules of logic. But what we have to realize is, it's not breaking the rules of the universe. It's breaking the rules inside our heads, our human, limited perceptions of how things should work. And this is maybe the most profound lesson of all. The universe does not care about our opinions. It doesn't care what we find sensible. It just is. And it operates according to a set of rules that are written in the language of mathematics. So when the math consistently gives us the right answers, we have to listen to it, even if it's telling us something that sounds completely insane.
And you know what? This isn't the first time we've been in this situation. For thousands of years, what did common sense tell us? It told us the sun goes around the earth. I mean, you can see it. It rises in the east, sets in the west. It was the most obvious thing in the world. But then, the math of astronomy started telling a very, very different story.
Why did we finally accept that the Earth orbits the sun? It wasn't because somebody flew up in a rocket and took a picture. We didn't have that technology. We accepted it because the math, the model with the sun in the center, was just unbelievably better at predicting things, like where Mars or Jupiter would be on any given night. The math just worked. The math itself was the proof. And it's the exact same story with quantum mechanics today.
And that's why I love this idea. Math is our sixth sense. It really is. It lets us see things that our eyes never could. It lets us perceive the warping of space-time around a black hole, the strange dual nature of an electron, the real architecture of our solar system. It reveals a whole layer of reality that's completely hidden from our normal senses.
So that just leaves us with one final, awe-inspiring question. If math has already unlocked these incredible hidden realities, what else is out there? What other fundamental truths about our universe are just sitting there, waiting for someone to find the right equation to bring them into the light?